I want to talk today about some of the research we've been doing over the last few years on Byzantine fault tolerance for collaboration software. And so this has got, it's got some security in it, it's got some decentralization in it, some distributed systems. And what I mean here with collaboration software, let's start with what I mean with collaboration software. What I mean is, you've probably used this type of software before, things like Google Docs or Figma or Overleaf or so, just apps that let multiple people work on some file or some data at the same time. It doesn't have to be a text document, it could be graphics, it could be a spreadsheet, it could be whatever kind of data. But the idea is that you've got several people editing this potentially concurrently. This type of software, of course, is incredibly helpful, and probably many of you use it regularly. But the way that this kind of software is built nowadays is in a very cloud-centric way, and I'm kind of trying to get away from that a bit. The other part of the title of this talk is on Byzantine fault tolerance, and so you're probably familiar with that, but just as a recap in case you're not, this essentially just means protocols that can tolerate some parts of the system misbehaving. And so what I mean with misbehaving is behaving in a way that is, somehow malicious or somehow is trying to break the rest of the system, trying to break the protocol. Formally, we just say that there are some nodes in the system that do not follow the specified protocol, in which case they may do anything, just send arbitrary messages to others, try to confuse others, and so on. Now, if you've built a web application before, it's probably in this sort of model where your web app is running on a central server, perhaps with a database, everyone else accesses it from outside. The number one security rule, if you're building an app like this, is never trust any data that you get from the client, okay? It's probably very familiar. Any data that is submitted by users via their web browsers, via their mobile apps, and that arrives via HTTP at your service is potentially suspicious, because users might try to do like cross-site scripting, they might try to do cross-site request forgery, they might try to do all sorts of interesting things by sending random, potentially corrupted inputs to your server. And so the idea with a web app is, you kind of have this barrier of application logic that you put around your service, where any piece of input that comes from a client, you validate, you treat it as untrusted, and only after you've verified that it matches certain criteria, then you let it in. You probably also have some authentication that happens there, which allows you then to check that the user is actually allowed to do the thing that they want to do, some authorization and access control. And the way how we do this in this sort of centralized server model is very familiar. And moreover, in the centralized server model, you have the authoritative copy of the data living on the database that is on your server, perhaps in the cloud. If you've got any sort of caches of the data on the user's devices, well, they're just that, they're just caches, they're not the authoritative. If you want something to be stored permanently, it has to go in the server, because the server's copy is what matters. Now, in the research we've been doing, we've been trying to get away from this centralized model, because there are many problems with the centralized model. One of them being, for example, that if the cloud service that you're using here decides to just change the app in some way that you don't like, or just decides to increase the prices so much that you don't want to pay for it, or just goes out of business, it's a startup and it runs out of money and they shut down with giving you 2 months to download a zip file containing JSON files of some data that you can't then import into some other service, well, that is quite a problem. And so what we would quite like is software where, it doesn't just depend on this one server. You can build it with one server if you like, but it would be very nice to also have the option of having multiple servers, so that, for example, if one of them becomes inoperable, you can just switch over to another one and just continue using the app. Moreover, it would be nice to also have the option of using peer-to-peer networks in here. Peer-to-peer is kind of difficult to make work reliably, because you have all these problems of two users might not be online at the same time. And so if they're not online at the same time, you won't be able to make a direct connection between those peers. So for that reason, servers are still useful and important as a way of sort of connecting users who are not online at the same time. But what we want to do is to move as much trust away from those servers as possible. Ideally, even end-to-end encrypted, so that the servers can only see ciphertext and no plain text of the data, and make the servers essentially as stupid as possible. Just make them things that forward messages along, but make sure that all of the actual data lives on the end user's devices. Now, this is kind of a nice vision, and a worthy goal to strive for, I think, but it now means that our security boundary that we had earlier no longer exists. There's no longer this nice place where we can draw a perimeter and say any input that comes from outside this is untrusted and has to be validated first. Because if it's peer-to-peer, any peer can communicate with any other peer, which might mean that the peers send each other potentially malicious data. And this is a problem because much of the research that has been done on this kind of peer-to-peer collaboration assumes trusted peers. They assume that everyone correctly follows the protocol. They assume everyone is being honest and nice. And unfortunately, that is not true. So I'll start with this kind of contrived example here, and then I'll give a more realistic example later on. So in this contrived example, let's say you've got a Google Doc-like equivalent, but that is peer-to-peer, and you've got two people negotiating the sale of a house. The seller and the buyer have a shared Google Doc, which is their contract, and there's a malicious estate agent involved in here. And now if you're a malicious estate agent, you could corrupt the document in such a way that the buyer sees one price in the contract and the seller sees a different price, and they think they're agreeing to the same contract, but actually the numbers are different. And this is, of course, a situation that we would not want to have happen. So what we want to do is to make sure that even if there's untrusted parties like this malicious estate agent involved in the collaboration on some document, nobody can corrupt the document in such a way that other users will see contradictory data. Everyone should be in a consistent state. So what you're thinking now maybe is, let's put a blockchain on it, because blockchain solves all of our problems. And so the idea here would be that you have some sort of blocks containing some sort of data. You probably have some Merkle trees in there somewhere that allow you to efficiently prove that some piece of data exists within this chain of blocks. And then you have some sort of Byzantine consensus protocol for deciding on the next block of the chain. Okay, and I will argue that this sort of blockchain model is fine if you want to make a cryptocurrency, if you're into that sort of thing. I'm not into them personally. I'm into collaboration software, and for collaboration software, I will argue that the blockchain is actually exactly the wrong model. It's precisely not what we want. The reason for this is that what a blockchain gives you is a total order of blocks, and this is important in a cryptocurrency because you want to prevent double spending. Okay, so you want to make sure that a user cannot spend the same coin more than once, and that requires ensuring that, well, two different spendings of the same coin, well, the one that happened first is the one that took effect, and the one that happened later, well, if that coin is gone, then that transaction won't even make it into the chain. So you require this kind of total order and this consensus protocol if you want to prevent double spending. But I'm writing collaboration software. I'm writing a text editor. I'm not trying to prevent double spending, okay? And if you're writing a text editor or a spreadsheet or something like that, what you actually want is a different model for merging concurrent updates. With a consensus protocol and a blockchain, what happens that if two users, or the same user with two different hats, make two concurrent, contradictory, conflicting updates, you want to keep one of them and throw the other one away. So if two people are trying to spend the same coin, only one of them can take effect and the other transaction gets ignored. In collaboration software, if I edit a document and also, well, I'll edit the document while my computer is offline, my colleague edits the same document while their computer is offline, then we come and merge our things. We do not want to keep one of them and throw the other one away. That is precisely what we don't want. We want to keep all of the users' edits and merge them together. And so a consensus protocol does not give us what we want here. We don't want to throw all but one of the concurrent updates away. We want to keep all of the updates and merge them together in a sensible way. Moreover, what we would like is that you can have different groups of users communicating through whatever network happens to be available. And so in this hypothetical scenario, you've got two blue users who are maybe in the same physical location and they've got a local network between them, and two red users who are also in their own separate location, and they also have a local network, and between those two groups of users is the internet. And so you could imagine, for example, the group of blue users working on their copy of the document and the group of red users working on their copy of the document and locally collaborating, even though the internet might be down right now, they might not be able to do the long distance communication, but you still want the collaboration to be able to continue locally within each of these subgroups while the system is partitioned. And then at some point the network will be healed and then everyone needs to merge their states back together again. So this is the kind of model that I want to enable. So where you can have subgroups of users collaborating using whatever network happens to be available. And then it's fine if users are disconnected from each other for a while. They should be able to merge together cleanly when they come back online. To formalize this sort of model, a colleague and I defined this consistency model that we call Byzantine eventual consistency. So you can see it's a very straightforward combination of eventual consistency from databases and distributed systems and Byzantine fault tolerance from security. And I'll talk a little bit about what we propose in this particular paper. The consistency model consists of three main parts. So these are essentially the properties that we want the protocol or the system to satisfy. The first one is that if an update happens on one user or one replica, then eventually all of the other correct replicas should receive that update as well. Okay, it's a fairly straightforward thing. It's like, imagine a gossip protocol, for example, that makes sure that every message is eventually received by all of the participants. But this is like the foundation. Okay, if different replicas receive different updates, then you can't do anything. So the baseline has to be, first of all, make sure that everyone gets all of the updates eventually. But we don't want to assume any timing guarantees on this. So it might be that you receive an update 2 days later, and that's okay. The second property that we want is convergence. And so that is, if you have two replicas or two users that have received the same set of updates, then they must be in the same state, even if they receive those updates in a different order. And that can happen, if you've had two users working disconnected from each other for a while and then merging their states together. And then the final property is to do with invariance. So ideally, we would also like the data to be able to preserve certain invariants. Now, this is a bit tricky because in this Byzantine eventually consistent model, not all invariants can be preserved. There are actually only certain invariants that can be preserved and certain other invariants that require consensus, and thus this much heavyweight machinery of blockchains, etc. And so I won't actually have time to talk about the invariants today. Maybe we can talk about that later if you're interested in that part of the story. I'm going to focus on the first two parts of this model, which is the eventual update and the convergence. So let's start with eventual update. So that is just making sure that all of the updates receive all of the users in a Byzantine model. So here we've got three nodes, A, B, and C. A and B are honest or correct, and C is Byzantine or malicious. And one typical type of protocol that is used in many distributed systems for like message dissemination and database replication and so on is version vectors or vector clocks. They're not exactly the same, but I'm just going to blur the difference for now. And the idea here is that each node in the system has a name. In this case, it's A, B, and C. And each node has a counter of the updates that it generates. And so you can say, for example, the update number 1 by replica C, and that refers to a particular update. And then if two nodes want to detect whether one has some updates that the other one doesn't yet have, then they can exchange these summaries, just say, I have 3 updates from replica C, which do you have? And the other one says, oh, I only have 2 updates from replica C. Can you please send me the number 3? And they send each other the number 3, and then everything is happy. Unfortunately, this does not work in a Byzantine system because, well, nodes can lie. They can send different updates to different nodes, but using the same identifier. This is called equivocation. It means just like saying different things to different people that are contradictory. And then this example here, node C makes an update number 1. So that's the ID of this update is C, 1, a pair of C, 1. And it says to node A, here I have update U1 with ID C, 1. And to node B, it says, here I have update U2 with ID C, 1. But U2 and U1 are not actually the same update. And so what happens now is that, well, A and B each store that update in their local storage, and then at some point later, A and B communicate with each other, and they say to each other, well, I have C, 1. Do you have C, 1? Yes, I have that one as well. Okay, we must be in the same state. Problem is they're not in the same state. They've seen different updates. And so now C has managed to make A and B inconsistent with each other, and we're exactly back in that estate agent example from earlier. So this is a failure of eventual delivery because in this protocol, unless we have some way of fixing it up, A will never deliver U2 and B will never deliver U1. So we want to make sure that they, in fact, do deliver these things. Now, how do we do that? what I'm going to assume now is that we have a protocol where nodes connect to each other pairwise, and you could say maybe that every node talks to every other node, or we can have a partially connected graph if you add a little bit more finesse to it. But this is the basic idea. Nodes connect to each other, and they want to efficiently figure out like which updates do they need to send to each other so that at the end, both of the nodes have seen all of the updates. And so here I have node A and node B. Node A has seen updates U1 and U2. Node B has seen updates U1 and U3. Now, the simplest protocol you could imagine is they just send each other the entire set of updates. Okay, that would be nice and simple. And that way, then they can then just take the union of those sets of updates, and then then they both have all of the updates. And that works. It's just really inefficient because the set of all updates that have ever happened in the system might be quite a large set. And so really what we want is some reconciliation protocol so that they can figure out just, well, B needs to send U3 to A, and A needs to send U2 to B. That's the minimal set of updates they need to exchange so that they both have all of the updates in the end. Now, fortunately, there's actually quite a simple protocol and algorithm we can use to achieve this, and that's what we talk about in this paper. We can make a hash graph. This might look superficially like a blockchain, but it's not actually a blockchain, as I will explain in a moment. It's much more like a Git repository. So in the sense that, in a Git repository, every commit has a hash of its predecessor commit, or maybe multiple predecessor hashes if it's a merge commit. And we can do the same thing here. Every update is encoded as a piece of data, and when you make a new update, you include the hash of the previous update, and that way you just make these chains of updates that are linked together via their hashes. And now nodes A and B only need to exchange the hashes of the most recent update. So A will send the hash of U2 to B, and B will send the hash of U3 to A. And now those nodes will see, we have different hashes, and we don't know each other's hashes. So now they have to work backwards in this hash graph in order to figure out which parts of the hash graph do they have in common, and which parts do they need to send to each other, that at the end they have all of the nodes in this hash graph. And so this is better now. At least you only have to start with exchanging the hashes, which are smaller than the set of all updates that have ever happened. But now with this protocol, we potentially have a lot of round trips, because these hash graphs might have very long chains where if many updates were done in sequence, and if it's a text editor, potentially every update is every keystroke that you type in your text editor, you can easily end up with a sequence of 100,000 updates if somebody's been typing for a long time. Now, if you need 100,000 round trips to bring these two nodes in sync with each other, that would be very slow. And so we can do something more efficient. The protocol we propose takes two ideas, really. The first idea is simply when nodes A and B synchronize, they remember the hashes of the most recent update at the time when they last synchronized. That's already helpful, because that means that the last time A and B synchronized, they saw that, they have this light blue graph here in common. And so assuming that nodes don't forget updates that they've had previously, that means that at least that part of the graph will be in common, and we can move on from there. Now, since the time A and B last synchronized, A will have added some subgraph of this hash graph, and B will have added some different subgraph. And so now we want to figure out exactly which nodes in those hash graphs do they need to exchange in order to get into the same state. And we can do this in quite a simple way with Bloom filters. You might have heard with Bloom filters before. It's like a way of probabilistically encoding a set in a small number of bits. And here, A can construct a Bloom filter representing all of the updates that it's added to its hash graph since the last synchronization. And B does the same thing. They send each other those Bloom filters, and that allows them to determine exactly which updates does the other side not yet have, send those to each other. Then, of course, there's a possibility of false positives in the Bloom filter, so then you need another protocol round to fix up those false positives. But this turns out to be quite an efficient protocol, and it's pretty simple as well. And so that gives us a way of achieving eventual delivery in a way that cannot be disrupted by Byzantine nodes. Okay, so a Byzantine node can add arbitrary extra nodes to this hash graph, but it can't corrupt the graph in such a way that honest nodes will fail to synchronize it correctly. And that's a very nice robustness property to have. And we've actually put this into production use in a library called AutoMerge, which I work on with some collaborators. There's also a blog post explaining this more informally. But that basically ticks off the topic of eventual update. So you can see this is actually not that hard. The topic of convergence is a bit more tricky. And for this, I don't really have such a good answer yet. I've got some rough ideas, and I want to talk you through some of those ideas, taking a particular concrete example. So convergence, as I've written it here, is kind of abstract, because I might be talking about text documents or spreadsheets or any other type of data. What I want to actually talk about is the data that we want to converge about is an access control list. So let's say that we have some sort of ACL which determines which users are allowed to access a particular resource, a particular document, for example. And of course, we want that to be able to be updated. So users have to be able to add new collaborators or remove collaborators if they leave. And we want to make sure that even if users are added or removed concurrently, maybe on different branches of this hash graph, that nevertheless everyone will converge to the same state of who is actually allowed to access this document. If you're familiar with CRDTs, this is an example of a CRDT, a conflict-free replicated data type, which is essentially like a data structure that ensures convergence. If you have not heard of that before, don't worry, it's not important for the purpose of this talk. So this is our goal here. Who are the current collaborators on a document, or the current set of users who are allowed to access a resource? It might be a group chat as well, for example. Imagine like Signal or WhatsApp, you have these group chats and where you can add or remove members from the chat. So it might seem that the simple answer is, well, the current members are those users who have been added and not yet removed again. Okay? Sounds simple enough. Why don't we just go ahead with that? Well, it turns out that actually it's not that easy. And what I want to talk about here is some work from a work-in-progress paper. This one is not published yet. And we actually want to rewrite the paper because the approach we're using in this is kind of confusing. But if you're really interested in it, send me an email and I can send you the preprint. So this is work in progress and it doesn't actually properly work yet, but I'll sort of give you some of the core ideas anyway for a decentralized access control list. So what we want to do is, first of all, determine who's allowed to read some data and then who's allowed to modify some data. In terms of reading some data, in a centralized system, it's simple. Okay, yeah, you have a server, it checks the password or checks whatever authentication mechanism you're using for the users who log in, and then check your list in your database to see whether the user is allowed to access this object. Done. In a basic peer-to-peer model, you could imagine a simple model where access control is determined by having a token. So there's a secret token. If you know the secret token, then you're allowed to read the document. If you don't know the secret token, you're not allowed to read it. This kind of works as long as you never want to remove collaborators, because if you want to ever remove collaborators, then you would have to change the token and give it to all of the existing collaborators except the one you're removing, or something like that. It's kind of messy. So really what we would like, ideally, is a world where there's end-to-end encryption everywhere, just like in Signal or so, and there's a decentralized access control list, so different users can update the access control list, and everybody converges to the same view of who the current group members are. So that's for reading. For writing, likewise, in a centralized model, it's simple. The server just checks, is this user allowed to write to this document? And if so, accept, otherwise reject. In a decentralized model, if we have peer-to-peer or not just a single server, then every peer has to check against this access control list, right? And so a peer might turn up and want to modify a document. Every peer who is talking to needs to then independently check this access control list to determine whether to accept those proposed updates or not. So it complicates the matter significantly if we're in this kind of peer-to-peer model. A bit more about the requirements for this decentralized access control list. So I'm just going to use a simple model where we say that there's a group. The group is the set of users who are allowed to access this resource. The creator of the group, or the creator of the document, the resource, is allowed to access it. They are an admin by default. And then any admin, any existing admin is allowed to add or remove other admins. This is kind of the most minimal model you could imagine that would work in practice. Really in practice, what you would want is some distinction between admins and non-admins and so on, but I'm just going to elide that for now. It turns out that even if we just restrict it to admins, it's already hard enough. So let's just consider only the world where there can be multiple admins who can add and remove each other. The other requirements that I want to impose here are, first of all, no server or any trusted authority, so it has to work in a purely peer-to-peer model. also don't want to assume like a blockchain or such like infrastructure if we can avoid it. It must tolerate users being offline, so it has to work independently of network connectivity. Any user who's not an admin should not be able to modify the group state in any way, which seems kind of obvious. And moreover, what's hopefully kind of obvious is everyone should agree on who the admins actually are. This is subject to the assumption that everyone has seen all of the updates. But this is the convergence property of Byzantine eventual consistency, right? So this is saying that once everyone has received the same set of updates, at least then they agree on who's actually in and who is out. So the approach I'm going to use here starts off quite straightforward. So let's just assume that each user has a cryptographic key pair, asymmetric key pair with a private and a public key. Assume there's some kind of PKI by which users know each other's public keys. I'm not going to touch on that in this talk. And then we're going to have 3 operations that the users can perform. A user can create a group, a user can add a member to a group, or a user can remove a member from a group. We're going to use digital signatures to authenticate these operations. So whenever a user performs one of these operations, they just sign it with their private key so that the other users can verify the signature with their public key. And then they broadcast that update through some kind of protocol. For example, that hash graph reconciliation protocol that I talked about earlier. This would be a suitable thing to use here to make sure that all of the operations are received by everybody who needs to see them. And then our set of group members should be some function of the set of operations that you've received. So each peer needs to locally be able to make a decision on who the current group members are simply by inspecting the set of create, add, or remove operations that it has seen. Okay, let's work through some examples to see where the problems lie. So in this example, there are going to be 4 users. They're called Alice, Bob, Carol, and Dave. And they each have a public key and a private key as specified here. And our first operation in this example is going to be Alice creates a group. And so she just creates this tuple of create, comma, the public key of Alice to say who's creating the group. Maybe she includes a group name or something like that, some sort of ID as well, doesn't really matter. And then she signs that with her private key. And now we have the first operation. And at this point, the set of group members is just Alice. Or rather, I'm going to write it down here as the public key of Alice, because we can identify group members by their public keys. Okay, so far so simple. Now let's say that Alice adds Bob to the group. So now Alice constructs a new operation. This operation is going to reference the hash of the group creation operation so that we know in which order the operations happened. This hash will turn out to be quite important later. So it partly helps with the dissemination of the updates so that we get this hash graph like I talked about earlier. But actually, it's also very useful in order to detect the time relationships between what things happened in which order. So here we have an add operation, which is this 4 tuple, contains token add, the public key of Alice, who generated this operation, the public key of Bob, who's the user being added to the group, and then the hash of the predecessor operation. This tuple gets signed by Alice, and then it's a valid operation. And at this point now, if you've received these 2 operations, hopefully you will agree that the set of group members is Alice and Bob. Now, let's say that 2 operations happen concurrently. So Alice on her device adds Charlie, while concurrently Bob on his device adds Dave to the group. And so now we have 2 different operations that both have the same predecessor hash. That is fine, no problem with that. We don't require a total order of operations. It's like a git commit history where you can have branching and merging. So here we have the form of these add operations is exactly the same as before. Alice's operation is signed by her. Bob's operation is signed by him. So at this point now, when you've seen these 4 operations, what is the set of group members? Again, hopefully uncontroversial that at this point the set is Alice, Bob, Charlie, and Dave. So even though Charlie and Dave were added concurrently to each other, those 2 operations are not in conflict with each other. We can just take the union of the set of group members, and it's reasonable. At this point, the group now has 4 members. Okay, so far this has been quite easy. Now let's add a removal operation. Let's say that at this point, Alice wants to remove Bob from the group again. So Alice originally added Bob, then Bob added Dave, and then Alice removes Bob again. But you can see here that the operation where Alice removes Bob, it now has 2 predecessor hashes, the hash of op3 and the hash of op4. And this is saying it's like a merge commit. It's saying that this removal operation happened causally after the 2 add operations. So implicitly, this means Alice here is acknowledging that both add operations were valid. So at this point, I will say that the set of group members should be Alice, Charlie, and Dave. Alice, Carol, and Dave, but not Bob. Bob has been removed. What about Dave? So Dave was added by Bob, and Bob has been removed. So should Dave be removed as well? I will say not, because at the time when Bob added Dave, Bob was a valid group member, and Bob had the authority to add Dave, and now Dave is also a valid group member. And then the fact that this removal operation of Bob happened after the time when Bob added Dave means that the removal happened causally after Bob's addition of Dave, and therefore Bob's addition of Dave continues to be valid. It's still valid even though the user who added them was removed. And I think this is a sensible thing to do, because you can imagine in a company, for example, it's the IT department in a company, and people come and leave the company, people get added, people get removed. At some point, maybe even the founder of the company leaves and gets removed and is replaced by a different manager, and that's fine. So the system needs to be able to evolve in a way that even the original group creator can get removed. Now, so far it's all been nice and everybody has been following the protocol nicely, but this is access control here. People might be malicious. We have to assume the possibility that, for example, a user needs to be removed, but they don't want to be removed. A practical example would be that maybe somebody got their phone compromised. Now the adversary got hold of all of the secret key material that's stored on that phone. And so now the adversary wants to continue having access to the resource, while the legitimate users want to lock out the adversary by revoking the access from that compromised phone. And so now you've got potentially this conflict between the legitimate users and the adversary, and we now have to be able to resolve those potentially conflicting situations. So let's look at this example. We start as before. Alice creates the group, and then Alice adds Bob to the group. And then let's say that Alice removes Bob again, maybe because Bob's phone got compromised. So at this point, it should be just Alice left in the group. But Bob, or the adversary here, the adversary acting as Bob, because the adversary has got Bob's secret key, the adversary now wants to continue having access to the group. And so what the adversary does is add a secret extra user to this group, add user C, where C is actually controlled by the adversary as well. And so this way, even though Bob has been removed, C, if this addition of C is a valid operation, then that would mean the adversary continues to have access to the resource through controlling the key of C. And this would be problematic, right? In particular, even if the device was revoked first and then the adversary started using the stolen key material, an adversary can always backdate. So they can always say the predecessor hash of this operation is somewhere in the past. And so the adversary can make it look as though the removal of Bob and Bob's addition of Carol are concurrent, when in fact they might have not actually been concurrent in reality, but just looking at the hash graph, we can't tell the difference. So here we have a possibility that while Bob is being removed, concurrently the key of Bob starts doing actions that he actually shouldn't be able to do. And so therefore I will argue that if we see this set of 4 operations here, the set of group members should be just Alice. So Carol should not be a group member here, because the addition of Carol is concurrent with the removal of Bob, and Bob was the one who added Carol. So if Bob tries to remove or add somebody concurrently or after their removal, after Bob's removal, then those operations should not take effect. But if Bob did some action concurrent that is causally before Bob's removal, then that operation is valid. Now here, this is already tricky, but I think we have a reasonable outcome. Let's make it even more tricky. We start as before, so Alice creates the group, then Alice adds Bob, then Alice removes Bob again. So far it's the same. Now what if the adversary, acting as Bob, generates this operation where Bob removes Alice? Now in general, this should be okay. Just because Alice created the group does not mean Alice can never be removed from the group. So it has to be possible to remove Alice. But now we're in this situation where we have 2 concurrent removals that are both trying to remove each other. So we've got a cycle between those revocation operations. And now what? What do we do here? It's particularly tricky if the group actually contains more than just those two users. So let's say A removes B and B removes A concurrently, but if the group actually also contains C and D, well, now it could happen that C and D sees those two operations in a different order. So let's say maybe user C first saw Alice's removal of Bob, and so then C removed Bob from the set, so it's only A, C, and D remaining. And then user C sees the operation from Bob removing Alice, but at this point Bob is no longer a valid group member, and therefore Bob is not allowed to perform this operation, and so that operation gets ignored. However, user C might see them in the other order, so maybe user D first sees the operation where Bob removes Alice, and therefore Alice is removed from the set of group members, and then later when Alice's removal of Bob arrives, then that operation gets ignored. And now these two, C and D, have ignored different operations, and as a result, they now disagree on who the set of group members are. And so now we've violated our convergence property that we are trying to achieve, okay? We have to make sure that even if two users concurrently revoke each other's access, and regardless of which order the users receive those update messages, everybody needs to at least converge to the same set of group members. So how do we resolve this? And we went through a long list of potential ways of doing this. Like in distributed algorithms, typically what you would do in this situation is attach a timestamp to every message, maybe a logical timestamp, and then just pick the one with the highest timestamp as the winner. Unfortunately, that doesn't work in a Byzantine system, because if you're the adversary, you can just pick a bigger timestamp. Just pick maxint as your timestamp, and then you can always win this comparison. So that's not going to work because it's not robust against adversarially generated messages. Okay, what about if Alice and Bob remove each other, we just remove both of them? Okay, that would be fair. Both Alice and Bob gets removed. Everyone agrees on the set of group members is now whatever it is without Alice and Bob. Unfortunately, you can end up in a denial of service situation where all of the group members get removed and nobody's allowed to access the resource anymore. And then what happens? I don't know what happens then if this is like controlling the infrastructure of a large company or something like that. Have fun. So that doesn't seem like a good solution either. Okay, we could say if Alice and Bob concurrently remove each other, those two removals cancel out and neither of the removals happen. And so Alice and Bob both remain group members and they have to perform additional operations to try and resolve the situation. But then that just really doesn't work either, because now if Bob is actually the adversary can always cancel out their removal. So if you're trying to revoke this mobile phone which has been compromised, and the adversary has got the key material on that phone, they can always cancel the revocation of that phone and thereby continue having access to the system. So removing neither is not really an option either. Okay, I mean, we could say like, oh, just give up, just pick a trusted server, whichever operation is received first by the server is the winner, and whoever gets there later, then tough luck. And so the honest users just need to try and be quick and try to contact the server first before the adversary is allowed to contact the server. And yeah, okay, I mean, it resolves the conflict, but it's not satisfying. It's not decentralized because now we've introduced this trusted server into the mix. And moreover, like resolving just based on who happened to get their message to the server first, that doesn't seem like a right answer as well. We want some way of resolving it so that the honest users can win and so that the adversary loses. Okay, we want to proper fight of black against white here. Okay, what about we take a blockchain smart contract, and that will solve all of our problems, won't it? And maybe it does. Maybe one of you can come up with a smart contract which does this. I've not been able to figure out how to do this, because the problem is, the smart contract itself will have some set of keys which are allowed to control it. And so you have to somehow keep the set of keys that are allowed to control the smart contract consistent with the set of group members according to our group membership algorithm, which is the whole point of why we're trying to do all of this in the first place. And so, yes, you could use some sort of out-of-bound mechanism, but then that doesn't really solve the problem either. We're trying to figure out who are the group members, and as far as I can see, a smart contract doesn't really actually help us answer that question. Moreover, blockchains are slow, and you have to wait a while for the next block to be mined, and then you have to do something in the meantime while you're waiting for that decision to happen. So, kind of reluctantly, the best thing we could come up with so far is we make a seniority ranking of users. So we say that the user who created the group is seniority 1. Any user who was added by a seniority I user has seniority I plus 1. And so therefore, if Alice created a group, then Alice is seniority 1. Alice added Bob. Bob is then seniority 2. And then if you have a conflict between people, users of different seniorities, then just make the most senior user win. In this case, Alice, as the group creator, would always be able to win this conflict. And at least it's deterministic. At least it ensures that everybody ends up in a consistent state. You have to handle the case where 2 users have the same seniority. This could happen if they are added concurrently. But in that case, you could just order them by hash or something like that. If you take the hash of the operation that added a particular user as their identifying hash, then that's a hash that the user themselves cannot tamper with because it predates, the creation of that hash predates their own addition. And so you can't try and mine the hashes so that you end up with the bigger one or so. So I think this ends up being secure, but it still has the problem that the most senior user cannot be removed against their will. So if Alice's phone gets compromised and the adversary gets hold of the keys on that phone, well, you're kind of stuck because you can't forcibly remove Alice's phone because the adversary, Alice, can then always remove the other person back harder, essentially, and win this kind of conflict. So then maybe what we should have is some sort of voting procedure, some sort of way by which the current members of the group decide if there's a conflict between 2 concurrent removals, which one should win and which one should lose. But voting is really difficult in this sort of context because you have to prevent Sybil attacks, because an adversary could just add 10,000 users to the group and then let all those 10,000 users vote. And of course, you need to make sure that the adversary can't simply win every vote by adding 10,000 users. So the problem is here, the users who can vote in this conflict resolution algorithm are the group members, but the point of the algorithm is to determine who the set of group members are. So the problem kind of recursively depends on itself. You need to determine who the group members are in order to determine the set of group members. It might be possible to resolve this somehow, but if you have great ideas, I would love to talk to you about this. There's also just usability problems in here. So if you have a vote, that means you need user input. The human has to say, should Alice be in the group or should Bob be in the group? Because there's a conflict between Alice and Bob. And how's the user supposed to know? Because if this is a compromised device, it's possible that Alice's device got compromised, or it's possible that Bob's device got compromised. How are you supposed to know? Maybe you will chat to your colleagues and figure out oh yeah, Alice lost her phone. Okay, we should revoke Alice's phone. But that means you need some sort of out-of-band communication. It means it's potentially vulnerable to social engineering attacks, where somebody might come along and just try to trick the users into voting the adversary's way. So it's really not obvious how you would handle these kind of voting things. What seems like might work is a sort of hybrid model where you say that we take this seniority ranking based approach for conflict resolution, except the most senior user is special. The most senior user is not actually a single user, but it's some sort of secret sharing scheme where some subset of users, say k out of n, can generate a valid signature on behalf of the most senior user, which can then override any other conflicts that can occur in the system. But still, this doesn't entirely solve the problem, because you need to evolve the membership of the secret sharing scheme as the set of group members evolves. So as you add a new member, you might want to add them to have a share of this secret. And as you remove people in particular, you'll be able to remove them from this secret sharing scheme. So there's still this problem of keeping the secret sharing, which acts as our voting mechanism here, essentially consistent with the underlying access control list. And that is basically all I know about this problem. So I'm going to just kind of leave you hanging there with this sort of open problem where we've tried to achieve this goal of Byzantine eventual consistency. I showed you that the first property of making sure all of the users eventually receive the same updates, that property was quite easy to achieve. It was not too bad. But the harder problem by far was trying to achieve convergence. And so here, I used as example of convergence this access control list where we were trying to get all of the users to just simply agree on who's allowed to access this thing or not. And even that turns out to be really quite hard once you allow concurrent updates and once you allow Byzantine behavior. And so that is just one example of an algorithm that you might slot in for this convergence piece of the puzzle. For other types of data, if it's not an access control list, but actually the characters in a text document also, we have different methods for that. That's a whole separate line of research, but I think that probably leaves us with enough to talk about for today. So that's all I have. Here's a list of papers. So the top 2 papers are quite directly relevant to what I talked about today. The other papers are a little bit more further afield. The last one here on local first software is not really a security paper, but it just articulates our vision for these kind of decentralized systems where the users control more of the data. So yes, that's all I wanted to talk about, and I hope we can have some time for questions now. Thank you very much.